one's stable now.
There's not where I said this one. Why is this chair rickety?
Why? There's supposed to be like 4 points of contact on the ground. Have you also the exam's been released? The
Yeah, the timetable.
22nd.
Yeah, that's a bit too soon, no?
Yep, that's wait. I put it into my phone. That's
27 days, 26 days.
29 days. 26 days until the 19th.
Is it? Oh, right.
Yeah. So we have just over 4 weeks for monetary.
This is a rough module. Are you at all prepared in the slightest way? Don't even joke that.
I'm gonna start revising next week for everything.
I'm massively behind on everything.
Like,
I'm so worried I was going to be. I sprinted over here. I actually can't hear you.
oh, you can hear what I said. I was just saying the second day we're doing stuff in here.
Oh, right, yeah.
Check. Where's that?
Okay, so I'm going to start. So make sure that we complete whatever we need to do. Also, you have access to the course evaluation forms, I think. If you could please complete them with as much detail as you want, that would be useful. I'll try and say that a few times in class. Okay, now questions on what we've done so far. Anything that you want to ask? So what we want to do today, so yesterday we set up the framework and we said that the trading, we saw what trading gives you, etc. And then we asked what would a planner do if the planner had full information, asymmetry of information. We found that solution. And then we provided conditions under which that same solution was incentive compatible, which is to say that if agents were asked to reveal their types, telling them what they would get based on what they announced, then they would be truthful in revealing their types. This is what we did here. And we said that, all right, this object called a demand deposit contract with sequential service will allow you to obtain the planner solution in the economy. So we need to define a few things. So fractional reserve banking is what we're going to talk about. In order to save on time, I will sometimes just make changes directly on the board. But of course you have all of this in the notes. Fractional reserve banking, in fact, we're going to call it a demand deposit contract. With a sequential service constraint. See what we mean by that. Is given in the following form. Okay, so 1 is deposited at t equals 0, and what you get back is specified in the form of a rule. So it's C1 Fj R1 is equal to R1 in certain circumstances, and it's equal to 0 otherwise. So what are the circumstances? If we still haven't said what fj is. I will say so in a moment. If afj r1 is strictly less than 1, this is withdrawal. At t equals 1. Okay. Again, at t equals 1. Fj is the fraction of total deposits withdrawn before J reaches the counter. Okay, and I'll explain this in a moment. C2 of F and R1, it's again F, not Fj, is the larger of, and I'll explain this, R1 minus R1F divided by 1 minus F, 0. Here F is again the fraction of total deposits withdrawn. By that we mean withdrawn at date 1. Okay, so what's the idea? So R1 is what your contract promises. Okay, that's what's written down. But the contract also stipulates that you will get R1 provided the amount that was withdrawn before you got to the counter is strictly less than 1. Okay? So the fraction of all depositors, the fraction being between 0 and 1, times R1 has to be strictly less than 1. Then you will get R1. Otherwise, you get 0. Right? At the end of period 1, once you move into period 2, by then you know what fraction had been withdrawn at date 1. So R1 times that F has already been withdrawn. 1 minus R1 times F remains. Think of it in the long run technology. That gets returned capital R, and that gets distributed over everyone who has not already withdrawn. Right? Provided it's not negative. If too much has already been withdrawn, then you get nothing. You don't get penalized by having to pay again at t equals 2 because of other things that happen. Is it okay? All clear? Yeah? So that's a fractional reserve banking contract. And now in red, I'm going to make changes to say how we use this. Okay, so supporting the ex ante optimal solution. Okay, so the planner's solutions. How do we support that? Well, we simply specify that R1 is actually C1 star. Is it okay? The contract is more general, that's the point. The contract, of course, could apply to all sorts of problems. In our problem, this will be C1 star instead of R1. Similarly, we here C1 star. Where C1 star, we've already found this. Okay, so if the fraction that actually will draw at date 1 happens to be pi 1, then what you will get back there, okay, right, in the following form: C2 of pi 1 and C1 star will actually be equal to, or there's another way to put in the notes, I just realized it might be a better way of writing it. Is that okay? So you will get exactly what you want if you specify R1 to be C1 star and if you can ensure that the fraction that withdraws is pi 1. And I star is the solution to the problem. 1 minus I star will be put into the storage technology because you know that is what you need to use to fund consumption of the early types. And I star is invested in the long-term technology. Over here, remember, since there is no liquidation cost, you can actually put everything into long-term technology as well. Doesn't really matter. Is it okay so far? Now, by the self-selection property, agents behave truthfully provided the promises that are made can be kept. Okay? So now, in any realization of this economy, so realization of this economy is where for every agent you specify their type. By the strong law of large numbers, which I've said earlier, cannot actually be applied here because to actually do this, we are thinking of a framework where each point between 0 and 1 is an agent, and the strong law of large numbers depends on the property of independence. Independence behaves very badly in that framework. So we assume now that in any realization of this economy, so with probability 1, the fraction of people who turn out to be of the early type is exactly pi 1. That's an assumption. Okay? We make some claim in terms of using the strong law of large numbers. That cannot really be done. So over here, it's really an assumption. Okay? So, I'll go back to black. Realization is really an assignment of types. So that's also. Pi 1 actually is what you will get in just about every realization. So if that happens, hence, if j equals pi 1, then fj c1 star, this is the key point, happens to be pi 1 c1 star, which is actually equal to 1 minus I star, which is less than 1. So this we know from our constraints, the Goodland's problem. Okay? That is to say that if all the early types, the fraction being pi 1 in general, if they are the ones who show up, then of course the bank will be able to make the promised repayments. What about the late types? If the late types behave as though they will be able to get their money back by waiting another period, then they will. Okay? So if the late types believe that the bank will be able to meet its obligation, that says in the notes, then those beliefs are fulfilled and the late types will prefer to wait. And that tells you, so this is a pure strategy. We haven't specified all the details, so it's a pure strategy based on Nash equilibrium. I should say that when this paper was written, this stuff was still fairly recent in economics. The concept of these notions actually goes back to some work done by Harsanyi, who also won the Nobel Prize for that work in the late 60s. It started picking up pace in the mid-70s in economics, most of it in game theory and its applications by the end of the 70s. And this is the early 80s, so that is still, people were grappling with these concepts at that stage. It was very clear. Yeah?
Is that Fj C1 star equals I1 C1 star? Or
Yes.
Yeah, that's an equals.
Okay. Actually, I'm writing it as Fj. This is actually, it should be F. I've written it as Fj in the notes as well. It should be F.
Just F generic.
Yeah. So but Fj will be less than or equal to F here. So, so it'll be fine. So I'll write that as F. Better way of doing it. I don't know why I wrote it as Fj. Unless that's the way it's in the paper. So I don't remember, now I need to check. Now, but the problem is, for any f such that f R1 or fc1 star here exceeds 1, liquidation at t equals 1 is insufficient. Okay, because think about it. This is the most direct way to think about it. The most that the bank can produce is 1 unit per capita. It cannot produce more than that. Because that's the endowment. Right? At date 1, the technology is not productive. So even if the bank were to liquidate everything that it had, whatever it is in storage, whatever it has otherwise, it cannot produce more than 1. Okay. And FC1 star larger than 1 will mean that you cannot meet your repayments. Okay? But your capital resources at t equals 1 is no more, let's write it as 1, is 1 unit. Correct? But while since C1 star exceeds 1 by assumptions on you. This we pointed out on Tuesday. The amount that the planner is promising at date 1 exceeds 1. Now it's clear that for f close enough to 1, you will violate the property. Hence, for f close to 1, but less than 1, we have a problem. This is what we mean by a run. The fact that you've promised agents at date 1 an amount that exceeds 1, so on average, you've promised them more than what you have in store, tells you that if more than the fraction pi 1, it need not be everyone, but if more than the fraction pi 1 decide to go to the bank, and it really depends upon how many more, not just any number larger than pi 1 will not work. Okay? But if it's sufficiently large, and there is a number that's between 0 and 1, between pi 1 and 1, which is large enough, whereby the bank will run out of resources, and then of course day 2 payments will be 0. And viewing that, everybody will run to the bank. Okay, we have a problem, and that's a run. Yeah.
Alright, I'm gonna essentially repeat what you said.
Yeah, that's fine.
Understand what you said, just so I can wrap my head
Yeah,
around it.
yeah.
I1 is a fraction of some number of early types in the economy.
The correct number.
The correct number of early
Yes.
types, right?
Yes.
The optimal number of early types?
No, it's, okay, so here's the point. Every agent becomes an early type with probability pi1. That's given to you,
Okay.
right? Now, a realization of the economy specifies the type of each agent. We are assuming that in any realization, or think of it as in just about any realization, that's great to think about it, the actual fraction of early types will be pi1.
The fraction of early types?
Yes, will be pi1.
Is that pi1 isn't the number of early types? It's a fraction of that amount.
So, this is the way you want to think about it. The two of you could be of the early type or the late type, each with probability pi1.
Yeah.
Correct? Now, it's quite possible that in a realization both of you are of the early type. Right? But if I have many people here, you would expect that as the number of people grows, and each of them is of the early type with probability pi1, and these are independent realizations,
Yeah.
you would expect that the fraction of people who are of the early type in any realization, almost any realization, is pi1.
Okay, all right. Yeah,
You agree?
Yes.
The problem now is, for technical reasons, we need to work with a framework in which we do not have a finite number of agents or even a countable number of agents. We are in a framework where you have a continuum of agents. Once you do that, the mathematics doesn't work. So we have to assume what we would like, which is that even so, in any realization of this economy with a continuum of agents, each independently being assigned a type, the fraction that turn out to be of the early type will, with probability 1, be pi1.
Okay.
That's the statement.
Okay. And F exceeds that amount, that fraction.
That's not good enough.
That's not good.
That's not good enough. What you see here is, since C1 star exceeds 1, there is a value of F sufficiently close to 1 such that FC1 star will exceed 1. This you know.
Yeah.
So what we are saying is, if for some reason the proportion of agents who claim to be of type 1 and go to the bank at date 1 is not just larger than pi1 but sufficiently larger, then the bank will become insolvent.
Okay.
Okay? And what we are saying is that all that you need is for a bunch of late types to believe that the bank will become insolvent,
Yeah.
so that they all run.
Yeah, so we're
And you cannot eliminate that. That's the only point. So there is a second, okay? Second pure strategy Nash equilibrium. We are not specifying it in any great detail. As I've said, I haven't even told you, specify it as a Nash equilibrium in terms of the details of what you need to do in terms of strategy and things. That becomes more messy. Okay? Yeah. You've probably seen this with Peter, either in micro or in game theory. If you've done that, you need to define types, map functions from types to actions, etc., etc. We're not doing any of that here. But it's caution. Okay, this can be done. Is it okay? So far?
Yeah.
Of course, what you notice is this is coming from fractional reserve banking, essentially. The problem is, so long as R1 exceeds 1, you'll have a problem. Any time that so any risk sharing solution which will make sure that risks are shared optimally, so the early types don't end up at the point at which they're making their decision on what to do, they don't know their type. So you want them to share risk. If you want them to share risk, you want them to benefit from the long run technology, even though they might turn out to be of the early type. So you want to give them a consumption which exceeds 1. You'd like to do that, because as soon as you want to do that, well, you're all right in the sense that that will be an equilibrium. You don't need a planner to do this. You can get it through the banking system, but you have this problem. That's the point. So far, what the paper is doing really isn't anything magical. It's all right. They're simply pointing out something that actually you would have known even before. You just sit down and have a coffee. Yeah, this has to happen. They're specifying how it works. That's all that they've done so far. What they do next is actually the really interesting stuff. Okay, so now bank runs. We've shown that they can occur. Okay, we're not saying that they have to occur, but we're saying that it is a Nash equilibrium. So to that extent, you might even say they have to occur. Okay. One issue that they do not deal with. This is an important issue that they simply skim over. In this second outcome, the payoffs are actually very bad. You might end up getting nothing, which is worse than an endowment. So if you ask at the beginning as to whether you want to participate in this contract or not, it's not clear that you wish to. The only problem is specifying the participation constraint here is non-trivial. So they gloss over it, they don't say very much about it. Okay? Because what you have is a situation of multiple equilibrium. Whether or not you want to participate in this contract is not something that, as far as I know, economics still does not have a clean solution on that. Okay, when you have multiple equilibrium. This is why economists try to work with problems in which the equilibrium is unique. Which is, no, it's not here. Right. So, bank runs can happen. Bank runs are inefficient. Bank runs destroy risk sharing opportunities. All that's there. Whether they will happen or not, as I said, is not clear because we haven't said in any clear terms that it is in the interest of the depositor to participate in this game. We haven't shown that. Is that okay? So that's something you want to bear in mind. So it's not, probably not written out quite so clearly in the notes. But that's something that you want to bear in mind. So what can you do about it? So the first answer is suspension of convertibility. Now look at how nicely this works. So the idea is you change your contract by a little bit and you tell agents, it's not clear to begin with as to how this works, but you'll see how nicely it works. You tell agents that, look, our contract is like that, but a slightly different one. In what way is it slightly different? You tell the agents that, look, there is a maximal length of the queue that we will allow. Here you're saying something very different. Here you're saying anybody can queue up. You reach the counter and you find out whether you will get paid or not depending upon what was the length of the queue before you got to the counter. That's what this is saying. Now you tell them that, look, there is a length of the queue. We will not add anyone to the queue after that. Okay? In other words, at some point, the window drops. No more withdrawals will be allowed. Okay? So, include clause no more requests for withdrawal will be honored if Fj exceeds F hat, where F hat R1 is less than 1. Okay, so it looks very much like that, and yet it's different in an important way. Okay, so the contract, I'm writing this again, now is 1 depositor equals 0, C1 Fj R1 equals R1, provided Fj is less than F hat, 0, otherwise, sorry, this is less than equal. Okay, so over here the inequality is weak in the first one, over there it was weak in the second one. and C2 of F and R1 is the larger of, well, over here, what you will get is again capital R times 1 minus R1 and F, 1 minus F, or capital R, 1 minus R1, F hat, 1 minus F hat. Okay, the rest, Fj and Ff are as before. I'm not rewriting those. Right? Now, again, set R1 equals C1 star and choose F hat to be some point in, and you'll see why we're doing it this way, pi 1 R minus C1 star. It looks, you know, like Greek, Chinese, whatever your favorite language is at this stage. But it's just reverse engineering. There's nothing more, as you'll see in a moment. Choose F hat in this region. It's a range. Okay, and check. This you will check for yourselves. Check that the partial derivative with respect to f of the expression R1 minus C1 star f divided by 1 minus f is negative. So as little f increases, this object becomes smaller. Okay, which you should expect. If more people withdraw at date 1, less will be left over. Okay? Now, the fraction of actual withdrawals cannot exceed f hat. This is clear. F hat must be less than or equal to f. Sorry, right. F has to be less than or equal to f. Okay. The actual withdrawals cannot exceed the bound that you've placed. Okay? So that's the most that can happen, and therefore, this shows you that C2 star C2 of f and C1 star, as specified there, f is the smaller one, so this will be greater than or equal to C2 of f hat C1 star. You can also check by substitution. Check this yourselves directly. That C2 of pi 1 C1 star. I think you have the computation in the notes, so I'm not writing it out. It is exactly what the planner would give to the late type, while C2 at the upper limit there, that one, this is why I said this is just working it backwards. That's all that they've done. You see one star. So basically what you get is, if you were to draw this, right, you have 0 here. On this axis you have f, the fraction you actually withdraw. That's 1. Here's pi 1. And here you have that value, R minus C1 star, over C1 star, R minus 1, and here you have consumption, which is consumption in order, R minus C1 star F divided by 1 minus F. That value is C2 star. That value is C1 star. You curve that looks like. So what it's saying is that regardless of what people do, you set things up in such a manner, right? But you're picking f hat, remember. So long as you pick f hat in that range, right? If the correct fractions show up, then the people who wait will get C2 star. Even if more show up, so long as the number who show up, the fraction that shows up isn't too high, and you know what too high is here, they will get at least C1 star. If they approach the bank at date 1, the most that they will get is C1 star, provided it's not insolvent. They cannot get more than C1 star, and they might end up with nothing. But if they wait, the contract is promising them at least C1 star. Okay? To begin with, you would have thought this can't be a good solution. It turns out to be a brilliant solution. You tell people that, look, do not approach the bank, because if that were to happen, you will get nothing. You're being told that. Okay? And that is carefully chosen. It's chosen to make sure that since you will necessarily obey the bank's instructions, because otherwise you get nothing if you show up. Right? By obeying the bank's instructions, you ensure that by waiting you get at least C1 star. More than pi 1 can show up. We are not saying that exactly pi 1 has to show up. But we are saying that anybody else who shows up might as well have waited, because they're guaranteed C1 star. And if some more than pi 1 show up but less than f hat, then if they wait, they will actually get more than C1 star. In this range, you get more than C1 star, all the way up to C2 star. Yeah.
So before it gets to pi 1, let's say you're moving along
Yep.
that curve. So we're getting to that fraction of pi 1. Before that point, people get C2 star, guessing.
No. This is the range that you're picking for f hat.
Right, but like before it gets to pi 1, when people are
You're,
starting
you're not allowed to do that. F hat has to be in that range.
Okay.
So you're not saying what happens if f hat is less than pi 1.
So we're already at this point where it's bad.
So f hat is set in such a manner,
Yeah.
right, that it's at least pi 1.
Okay. It's at least pi 1.
It's at least pi 1. And it is at most that value which ensures that if f hat is the fraction that actually will draw at date 1, even so, what's left over will guarantee C1 star for anybody who waits. If they go to the bank at date 1, they will get C1 star. If they wait, they get at least C1 star.
Yeah.
All right.
So-
Okay.
So they'll wait. Is it okay?
Yeah.
It's very simple. If you think about it, it's actually very simple. They just worked it backwards, nothing else. But it's a very nice idea. And this is actually what the paper is about. The paper isn't so much about showing that you have models of bank runs. The paper is more about saying this is a model where a bank run occurs in the following way. And what we already know as policy instruments that can be used works if you set it up in the following manner, which can be analyzed within the same analytical framework. That's what they're doing.
Have bank runs occurred in this way?
Have bank runs occurred? Bank runs have occurred.
Well, they've occurred, yes, but
Yes.
like, have they
Suspension of convertibility.
in this way?
No, wait, what you're asking is, has suspension of convertibility been used? And the answer is no. Policymakers typically have been averse to using suspension of convertibility because they think it's a terrible thing to do to people. To tell them that you go to the counter and the counter drops. It's better to simply say that, no, you are at the counter, that's fine, but there's no more money. And what this is saying is it would be much better for you to codify this, because then you can prevent runs. Importantly, this is an equilibrium phenomenon. Be careful. Out of equilibrium, beliefs can be all sorts of things and things can go wrong. The paper does not develop that any further, but it's known that things can go wrong. That's a separate matter. But so long as people stick to equilibrium in this framework, Outside this, we need to formulate it, otherwise we can't really say. But in this equilibrium framework, if people stick to equilibrium behavior, then you're all right. Is it okay?
Yeah, that's fine.
I'm not going to say much more because with these things, my own experience is the more you try to explain it, the more you confuse people. It's better to try and explain it once, repeat the same thing as many times as I need to, and make sure that you understand what I'm saying. Beyond that, there are all sorts of things that you can talk about. You know, I start talking about examples, this and that, get into reality, it's a complete mess. That's why I don't want to do that. But there is something else that is also there in the paper which I want to turn to now. Okay? Is it okay? Can we move on? So, looking for that. So this was suspension of convertibility. But the thing that we tend to think about much more, so we have this one here, so actually no, so I'm going to erase things here, since you have everything on your in the notes. Now the thing that I've known about from the time I went to the US, but I was surprised that in the UK this was brought in as late as 2008. Some of you, only two of you here, sounds not a good, nice way of putting it, but you might know about the Northern Rock banking crisis, right? So the major financial crisis that we had in 2008, 8, 9, 7, 8, 9. That was the last major bank collapse in the UK, from what I know. There have been other bank runs in the US, even more recently. There was one on a Silicon Valley bank, I think 2 years ago. So that keeps happening. Okay, so it's a persistent phenomenon. Now the thing that I want to talk about is a form of deposit insurance. Now what we will see here is not quite that. They sell it as deposit insurance, I mean the authors. What they actually have is something which is a bit different. But so what deposit insurance does is banks are required to ensure, so there's a cost associated with it, that there's a certain fixed value, and every depositor is promised that regardless of what happens to the bank, that amount they will get back. Okay? And in the US, even 40 years ago, it used to be $100,000, regardless of what bank you were in. In the UK, this was introduced after Northern Rock, and if I'm not mistaken, the figure is, I think it's £20,000. You can check it very easily. But it's £20,000 across all your bank accounts. Okay, so it's still a very low value, but for small depositors, it's a lot. The problem with bank runs really has to do with small depositors who really don't know very much, and they trust the bank, and it goes under. It's a huge problem. So that's what deposit insurance does, but the way it works here is very different. Okay? The idea here is very different, because the idea here is the following. What it says is, and it's very easy to do. What it says is the government here, or the central bank, whichever way you want to think about it, will tax you after you've carried out your withdrawal at date 1. Okay? You see, the problem here is whether people run to the bank at date 1 in the hope that they can guarantee their consumption. The government is basically all powerful. This we need to remember, right? A famous example of this was when, with the Greek banking crisis or government bonds crisis in the early, about 10, 12, 14 years back, when Mario Draghi, who was chair of the European Central Bank at that stage, at some point when the crisis was really boiling over, he said something very simple. It's unbelievable. He just said, we will do whatever it takes, and everything calmed down. The whole problem vanished. Greece still has its problems, and it's going to come back again. So the point is the ability to commit, the credibility that it carries, is what's important. So the fact that the government is able to tax you after you've carried out your withdrawals at date 1, it reassigns consumption at that stage. And everybody knows that. So the people who are of the late types can sit back and say, look, it doesn't matter. The government will fix it for us. And since they say that, since they believe that, in fact, the government never has to do anything. Okay? So let me see if I can write that up. Okay, so this also works when the value of pi 1 is unknown. Okay? So everything that we did earlier worked with a known pi 1. Okay, so here also works when pi 1 is not known. So let pi bar be the highest possible value. Technically, this is called specifying the support of the distribution. Okay. Specify a tax function. Okay. So we're going to specify a proportionate tax function. So specifies a tax rate as a function of f, which is the fraction of total deposits withdrawn, and R1, which is the promise, and okay, so promise to contract. And the tax rate is 1 minus C1 star of f. Remember, the planner's solution depends on the fraction of early types, right? So over here, you don't really know what the fraction of early types is, but you can observe the fraction of total deposits withdrawn. So based on that, you can work out what C1 star is. C1 star f divided by R1 if f is less than or equal to pi bar. Okay, and now if R1 equals 1 minus 1 over R1, if f exceeds pi bar. Okay. After tax, what will you get? Well, C1, again, as a fraction, as a function of what fraction was withdrawn, and R1, which is promised, will be, well, R1 is what is promised, and then you need to pay the tax. Okay, so it's R1 times tau of f and R1, and this, it's almost trivial now, is C1 star of f 1. This is if f is less than or equal to pi bar. This is if f exceeds pi bar. Okay, by feasibility. C2 of f and R1 will be capital R 1 minus C1 star of f times f divided by 1 minus f, which you can check. C2. So please check these things. F, if f is less than or equal to pi bar, and it's equal to R if f is larger than pi bar. So this is, it's, you know, it's sort of the kind of maths that you do when you're 5 or 7 years old. That's all that you need for this, nothing more. Conceptually, of course, you wouldn't have been able to do that. Conceptually, even lots of very good economists would not have been able to figure this out. Okay. It's as simple as that. You're basically saying, look, the fact that you can tax, the power to tax, the power that the government has to commit to be able to tax is what counts. You can fix it. You can tax in such a manner that regardless of what anybody does, this is what's happening here, because what you do determines F. Your choice as an agent here is to whether you go to the bank or not at date 1. That's all that you do. You don't do anything else. So regardless of what you do, you will get C1 star of F. Or 1. Yeah?
What is the purpose of letting pi bar be the highest possible value of pi bar?
Otherwise you can run into trouble. Otherwise you can run into trouble. I haven't specified it here, okay? But basically you can run into trouble after another. But of course this also works when you know pi 1. Be careful with everything that you've done. That's important. And the people who want to withdraw at date 2, they're guaranteed at least C2 star because R exceeds C2 star by risk sharing. You will always get what you've been promised as a function of the true fraction who show up. Now this part actually kills the need to go to the bank for the late types. And once you do that, the early types will of course go to the bank. They're the only ones who go to the bank. In any equilibrium, that's what happens, and therefore the government never has to intervene. The power of commitment. Commitment to be able to tax. You have that power, you exhibit that power, that's the outcome. Okay, there's a unique Nash equilibrium. Okay. Yeah. Just about on time. Right. So we have our problem solving sessions. I'll talk about the exam, etc. over there. If you have any questions on this, we can take them next week. There's no problem. Again, I've said this. You're serious students. That's why you're here. Do not read anything else on this. Strong advice. Do not. If there's something you don't understand, read the paper. Come and talk to me. Talk amongst yourselves. That's fine. Do not read anything that tells you here's a simple way of understanding, because there is nothing else. I assure you. There are all sorts of other works, that the papers that have been written, nothing actually clarifies things any better than the paper that is very well written. And as I said, people think about this paper the wrong way, that it's a really brilliant model of bank runs. It's not. It's a simple model of bank runs, brilliant, that's all right. But the purpose is to use that model to analyze policy that's been used earlier as policy that could have been used. That's basically what it is. It's important enough that there are no, all the extensions that have gathered mileage are very technical in nature.